Right, with this topology we saw static and default route. When we write default route, we should have only one gateway. We should have only one gateway for all the unknown destinations. That is what I mean. When you want to write a default route, you need to have only one gateway for all unknown destinations. For example, on router A, when you see this is a known destination, this is another known destination. The unknown destinations are 30 and 40. We call this type of router as a stub router. So on stub router, where all the unknown destinations are in a direction, you can very well configure default route instead of writing 2 lines to say 30 network, go this way, 40 network, go this way. Instead of saying that, you can say for any destination that's not known to this router, anything that this router does not know, just forward it here. See, this is a small topology. You know it is 30 and 40 is what? Unknown.
Yes.
But in the real world or in the production or in the internet, we will not know. We will not know how many networks. Internet has got millions of networks. We cannot keep writing routes for every single destination. Not possible for us to know those destinations. And even if we know, writing is not a good idea for million network destinations. So simple. We just point our router. Let's say this is our organization and this is our edge router. Sorry, I finished coming. We just point, this is our edge router of our organization, and this is the ISP, Internet Service Provider. We tell the edge router, just go there. For anything that you do not know, go to ISP. ISP has got those millions of routes. That is the job. That is the service that they want to provide. They show us the route to all the destinations around the globe. So we, instead of writing all those million routes in our routing table, which is not possible, and even if it is possible, which you should not do. Another thing is the router that we have is not that big like ISP routers. So to accommodate those million routes, you need to have really a very big buffer, for which you need to spend a lot of money. Again, these are all not necessary. Right? So you simply use a default route saying go to ISP. ISP will take care of it. That is what called as default route. Now, what if I have few more routers and few more networks? Let's say I have 50 60 70. Now to this router 1, 60 70 is also unknown. Now, can I keep this default route or should I remove it? You can keep it. Why? Because these are just two networks and they are your own network within your organization. You know them very well. So write a static route to reach 70 and 60 pointing towards 50001. So even though this is not a stub router, your own networks you know very well, and there are not too many. You can write static route for all the networks that are in this direction, which is your own. And for all those unknown destinations in the internet, you can point towards the ISP. So can we write a default route and the static route together in a router? Yes, this is what the scenario. You have few networks, maybe 10 networks or 15 networks in your organization. That's not a big burden. It is easy to write 15 routes for those networks that are inside your organization. And for all other networks, which we really do not know but we want to reach, like Yahoo, Facebook, YouTube, no one know. Do I really don't remember any IP address of internet like Facebook or YouTube or Gmail or Yahoo Mail. I don't remember any of the IP address. Neither my laptop nor my router. But still I'm able to reach all those destinations. It is because my router in my home is just having a default route towards the ISP. That takes care of my packet. So when I ping from somewhere, okay, from this PC, 70001, the packet goes like this and it is delivered here by using the static route. When I ping instead of 70, 170, there is no 170 within my organization. So it uses this the default route, and delivers the packet to ISP. ISP knows everyone. Only then that is ISP. ISP should know every destinations, every network around the globe. Their job is to take our traffic to wherever we want and deliver it there. That is why we are subscribing to an ISP. We really do not know address of a new website that you are trying to log in today. You want to apply a visa to go to Finland because they give you 25 lakhs if you migrate to their country. Wow, we want to test it. 25 lakhs free just like that? Yeah. Now you want to see how to apply for a visa to Finland, and you go to Google and type what are the steps, and it shows a web page. You need to go to this web page and log in and upload some details. But what is the IP address? Do you think like that? What is the IP address to go to that visa page? No. You just click the link. Your PC sends the request to the DNS server, which the PC knows very well, asking what is this finland.us.support.com. Then it says, this is this IP address. We go to this IP address. Now, do I know the route for going to that IP address? No. but I just take that IP address and put it in my packet. And when I forward the packet to the router says, oh, this IP address we don't have in the routing table, but I have an option, any. I do not know. Anything that I don't know, I need to simply send to ISP. The ISP receives it, ISP knows it, it takes my web page request to view the Finland visa page, and I get the page downloaded. I see it in my computer, and I send all those documents and then got settled in Finland. See, any, yeah. So, default route, a CCNA level, they will say it should be written only in a stub router. When you have only one exit for all unknown destinations, we call it a stub router. That is where the default route fits in. Not 100% true statement. You see here, we had some unknown destinations, but we wrote a static route. Now all the destinations inside are known. Yeah, truly all the unknown destinations are now only on the right hand side towards the ISP. So we can mix both static route and default route. We can very well mix static route and default route so that all the unknown will be in one direction. Static route you have written for all those that are in the left hand side, and for all unknown destinations that are in the right hand side, which is a big internet. In our case, it's a big internet. We don't know how many million routes we need to write, and we don't know those destinations. We simply write a default route pointed towards the ISP. Is this clear for you? Static and default route?
Yes, sir.
Wonderful. Now, when we write a route, we have two options. One, we wrote like yesterday, show run. When we write like this, we are, instead of saying exit interface, we are giving the IP address of the next router. You see, now we are saying any network, any subnet mask, send the traffic to 20002. 20002. This is the IP address of the next router. What if this IP address changed? Your static route is not going to work. Static or default, whatever. It's not going to work if you are providing an IP address and if the IP address is changed. If router B changes this address, problem. So if router B is not your own router, we will not be knowing the IP address in the first place. If router B is not our own, if this is ISP, assume, if this is ISP, router 3, sorry, router B, router C, they don't belong to us. Ours is only router A. Then how will I write? How will I know the IP address of ISP?
We'll just give the router's interface exit.
Exit interface. Very well said. So that's the option we are going to do now. I'm going to remove saying no IP route, whatever I typed in the previous class. No IP route, any network, any subnet mask, go to this. This is what I wrote. I'm removing it. But before I remove, Let me put it in a notepad. I want to show you something before I remove. Okay, so I'm not removing now. I just delete it now. I'm not going to remove. I would like to show you the routing table. Show IP route, and here you see a star via 20002, and the number here you see is 1. But for the above two networks, you don't see such numbers. The reason is it is directly connected. For directly connected, the trust level is 0. Meaning, oh sorry, you should not misunderstand that. The trust level is too close. More trust means the administrative distance is 0. Administrative distance. Meaning, you don't need to take care of too much about it. You don't need to think about it too much because they're directly connected. They're well known. But this one needs a care. Why? You are saying go to this address. It is not directly connected. So we need to give some little care about this address. What if the address changes? So they have given the trust level as 1. More smaller it is, more you trust. 0 is very thin, small. For directly connected, it is 0. It's highly trusted. And when you say the next router's IP address, then it is 1. I'm going to write the same default route like this: IP route, any network, any subnet mask. Just send it out via F00, my own interface. Just push it out on this interface. Now, when you say this, how the packet will go to router B? When you say push it out on this interface, router A will check what is there on that interface, F00, this 20 network. And then router A will also check the adjacency table, who is there in that 20 network. Let me first ping, and I changed the default route, but still I'm able to ping. Okay, it's pinging. So I changed it. The old default route I have removed and I have changed it to exit interface. Now, what this will do, okay, 20 network, who is there in 20? Show R. Okay, on F00, 20001 is my own. In that direction, it is sending an ARP request. It has learned the MAC address of router B. This is actually the MAC address of router B. 40 is not directly connected to router A. In order to go to 40.10, it needs to go to this IP address. This MAC address. Whose MAC address is this? It is the MAC address of 20002. Let me show you. Ping 20002. Now also, if you see the ARP table, for 20002, it's the same MAC address. So using the MAC address, it can push the traffic to router B. Now that's how it works. Now let's check the routing table, show IP route. You see the difference. Earlier it was not showing directly connected, it was showing us one administrative distance in the bracket. One. This is zero. This is more trusted because it's your own interface. Earlier it was not my interface, it was a neighbor's address. If neighbor changes, then it becomes invalid. It becomes invalid. But now this statement will not go invalid. The static route that I have written is valid as long as this F00 exists. In case if I delete this wire, then I lose the line. It will go away automatically. See, it's gone. The static route is gone because I said go via F00, but F00 doesn't exist now. So it won't be staying in the routing table and causing trouble. If those routes that if that default route that I wrote is still there, then it's a trouble. It's a problem for us because there is no interface, and if the route is there still, and there is no interface, then packets will be trying to go out and getting dropped, which is not good. So the operating system can sense. The router can sense that the interface has gone down, so all that is related to the interface should be deactivated. Now it will come back again. The static route that I wrote has come active. Right now, these things, we should have this. This may sound like, it's logical. Yeah, it sounds meaningful, but you will forget these things. Static route. How can the static route disappear just like that? Yes, it will disappear because the static route that you have written is pointing towards interface. The interface is down. See, if I shut down the interface also, it will go off. Interface F0/0 shut down. Even now, you will not see the routes. Though there is a route, there is an IP address, but still, those networks are inaccessible because the interface is down. Now this comes back again. All right. Okay, so there is also one more option. Let us go to router C. In router C, I have given two static routes. Two static route. I can remove these static routes and write a default route. That's what I'm going to do now. I'm going to say no IP route. The easy way is go to the running configuration, copy those two lines to the notepad, and put no and no, copy it, and paste it. Even on the real router, this is applicable, not only on the simulator. The real router is much more easy. You just highlight it, it gets copied. You don't need to press a copy button or Control C. Fine. Now let's go and verify there is no route now. Show IP route. IP route, there is no route. So when you ping from this left hand side computer, this time it won't ping. It will say request timed out. The reason is the packet goes, but there is no response. When there is no root, then there is no chance of getting a response. This thing won't happen. What we need is we need to write a route, and I'm planning to write a default route. IP route, any network, any subnet mask. You see, I can give interface name. I can also give IP address. Let me try to say both. I'll say go via F0/0 and these don't have. But some operating systems, they do support both. I can say IP address, go to 30.0.0.1. Aha, it is allowing only one. But you can give both. When both are
Okay.
valid, only then the route will be active. And I was
Okay.
talking about the administrative distance. You can also provide the administrative distance. The default is 1 if you are giving an IP address. If you are giving an IP address to reach instead of exit interface, it is 1. But if you say no, make it a 2 or make it 20, then you check the routing table now, it is 20 in the bracket. So if there is another static route written by me, say I'm going to write another static route saying 30.0.0.30, which is not true. But I don't see this, I don't put this administrative distance, then which one will be there in the routing table? The one with the lower administrative distance. When I don't say any administrative distance, it is 1. Now if you check the routing table, for your surprise, you will see a wrong route pointing towards 30. Because the administrative distance 20 is less preferred compared to this. Lower the administrative distance, more preference is given. Both are default route, which one to take? The one with the lower administrative distance need to be taken. That is why it is coming like this. But we don't have 30.0.0.30. But still the route is there because we administrator have given the IP address 30.0.0.3 with less administrative distance, 0. But in the routing table, sorry, in the running configuration, you will see both. You have both 30.0.0.30 with the administrative distance default, 30.0.0.1 with administrative distance 40. It compares the administrative distance. When there is a tie, the tiebreaker is the administrative distance. There is a tie here. You see, both are default route. So it's a tie. So whether to go to this IP address or this IP address, I'll go to this IP address because the administrative distance is not given by me. The default is taken, which is 1. Though it's a wrong IP address I have given, but router will only prefer that because I have given the preference. How? By making this bad, I say this is 20, which means I'm indirectly saying this is the best. Because I, the administrator, have said it is best. It is shown in the routing table. So we can use the administrative distance to play when we have a tie. Otherwise, this administrative distance number is not necessary. Only when you have multiple static routes, it is needed. Only when we have multiple static routes, this is needed. Now, do you have any question regarding this static and default route?
No, sir.
Well done. Now we are moving on to a protocol, routing protocol. Static route is good in one way, but it is also bad. How? Static route is good because you have a very clear path. You have very clear information about what path it takes. We have very clear information about what path it takes. That's static route. What path it takes. What path the packet takes to reach the destination. Because you wrote them. But the con is you need to know the complete topology, which is difficult. Even if it is your own company, knowing if it's a big company, knowing all the networks and their locality and their location, to whom it is connected and what path, what all paths available to those destinations in your network is little bit difficult for everyone to know. Knowing the topology is very important. If you know it very well, then you may go with a static route. But what if you have less information about the complete topology? Then how will you write static route when you don't have much info of what network is connected where? Knowing the complete topology is important. If you know, then you can take a chance. You can write static or default static and default route. Again, if it is too large network, you may be a supercomputer, you may know the complete topology, but static route is still not recommended. Even though you know the complete topology, you know which network is connected where, you can write a clear path without making any mistake. Even though you are super talented, it is not recommended. Why? Because it's a large network. When we write static route, they stay in the routing table, even if somewhere down there a link is failed. When there is a link failure somewhere down there, only that router which is connected to the link will remove the route. But the other routers which is pointing towards that router with the static route will still keep holding the route, thinking that everything is normal. Because the routers which are not directly connected cannot sense the failure of the link. For example, in router A, I am saying, in order to go to 40, go to router B. And in router B, I say, in order to go to 40, you need to go to router C. Now, when this link fails, when this link between B and C fails, that static route that I wrote for 40 go towards router C, that gets removed from here. But what about this router? This will not remove, because in this router you said in order to go to 40, go to router B. Router B is available, but that is not enough. We also need C to be available. But C and B, there is a break in the wire. When there is a break in the wire, you cannot reach 40. But the route that we have written here is still available. Which means when I ping 40, the packet is going to go all the way down here and get dropped here. So the routing that was done here is wasted. The bandwidth got consumed and wasted because the packet got dropped here. See, this is just 3 routers. If I have 20 routers, At least 18 routers will get these packets and 19th router is going to drop. The process consumed on 18 router is a waste. The bandwidth consumed in between this 18 router path is a waste. So even if you are ready, even though you know the topology very well, if it is a large network, leave it to the protocol to control. Why? Protocol can sense it. As soon as it finds that there is a failure in the link, as soon as the protocol knows that this is gone, the link has failed, immediately all the networks that are via that link, all the networks that's supposed to go via that link, like 40 in our example, will be removed from every router, not only from B, even from router A. How? The routing protocol will inform B, the routing protocol in B will inform that, hey, those networks that is via my gateway 30, remove it. Dynamic routing protocol is going to inform the current status of every path. As soon as something goes wrong or if some new network comes in, immediately a flash update is going to be sent to everyone. A triggered update is going to be sent to every router notifying that such and such thing has happened. So all the routers will immediately tailor, alter, converge to the new change that has happened. Converging means adapting to the new change. Routing protocols can dynamically go and write a route into the routing table. Dynamically, it can remove the route from the routing table when there is a change. Because it is dynamic, when you now ping 40 from here, router A itself will drop the packet because router A knows that 40 doesn't exist now because there's a link failure here between B and C. The routing protocol can tell router A to remove it and router A will remove it. But if it is a static route, you need to log in to remove it. Here we got just 3 routers. You may say, I'll go and remove it, not a problem. But in the real network, in the big network, you may be sleeping, you work in first shift and second shift is in the office, and they're going to call you. To office because something went wrong in the network. But if it is a routing protocol, it would have done all this thing automatic. You no need to go to office. Routing protocol would have found another way to forward the packet if it is available. If there is another path available, it would have forwarded the packet via the other path. So dynamic routing protocol is the best when it comes to large network, big network, dynamic routing protocol. We have many dynamic routing protocols. The first one that we are going to see is called RIP, the Routing Information Protocol. RIP stands for Routing Information Protocol. This is a protocol which is mostly used in a very small environment. What I mean is, this protocol has got some limitations. So if you have a network, let's say with 10 to 15 routers, you may use this protocol RIP. Let me take a minute. We're going to learn routing information protocol. Routing information protocol RIP. This is well suited in a small environment. As I said, when you have 10 to 15 routers in your autonomous system, in your office, what is an autonomous system? Uh, a network that works for an organization is an autonomous system. The network that is governed by a single administration. The network that works for an organization. The networks, the devices that works combined together for one single organization, single administration. That's an autonomous system. So if your autonomous system, if your organization is small, it's not having too many routers, then very well you can go with this protocol, because this protocol can support up to 15 hops. So see, hop, every router is one hop from here to here, here to here, here to here. Now if I want to go from A to B, how many hops? 1, 2, 3 hops. Likewise, this routing protocol can support 15 hops only. Your destinations should not be more than 15 hops. A medium-sized organization, a small organization will fit in. Alright, so this is one point. This is a nice protocol. I'm not saying this is bad because it has got this limitation. This is a very nice protocol, but cannot be enabled in a large environment. Now, every routing protocol will come under some category. RIP comes under a category called distance vector. Distance vector. Distance vector routing protocol. RIP comes under the category called distance vector. Distance vector. What is distance vector? You see, this protocol is going to give you two information. One, the distance, like how many hops away, how many hop away, how many hop away. The destination is. How many hops away this destination that you are trying to reach is. And in what direction. When these two things are given, when these two things are advertised for every destination, by a routing protocol. We call that routing protocol as a distance vector routing protocol. A protocol that advertises these two things for every single destination. For example, now this router will tell that 4.4.4.4 is one hop for me and in this direction. This router will say same 4.4.4.4 is two hop for me. See, 1, 2. Two hop for me and it is towards router 3. So when this router 1 learns it, when this router 1 receives this update, now this router 1 will decide to use this path because according to router 1, now 4.4.4.4 is two hop away via router 2. You see, it is not via router 3. Via router 3, it will be 3 hop. 1, 2, 3 hop. This is the cheapest one, just 2 hop via router 2. So it shows both the distance, which is 2 hop, and the direction, which is via router 2. That is why the protocol RIP is called as distance vector protocol. It shows how far and in what direction. You understood why it is called as distance vector protocol?
Yes, sir.
Yeah, wonderful.
So, sir, another name for RIP is distance vector information protocol.
No, distance vector protocol is like a common name. Routing information protocol is like a proper name.
Okay.
Distance vector protocol is like an overall, a common name. It is not particular. One of the protocol of distance vector is RIP. So
Okay.
you may have, see, we don't have right now, but maybe there was some protocol which was behaving the same way, providing the distance and the direction. Even those protocols will also come under the same category called distance vector. The name may be different. So any protocol that will provide you these two information, they're called as distance vector protocol. So this is how the
Okay.
categorization goes. The RIP comes under the category called distance vector. There are other categories like link state, path vector, and so on. We'll talk about those things when we go there. There are other routing protocols that we'll be learning, like example, OSPF is a link state routing protocol. It is not a distance vector. BGP is a path vector routing protocol. It is not a distance vector. It is a path vector. So this is how the categorization, the global categorization. Okay, now
Yes, sir.
RIP is a distance vector protocol, and we see here RIP has got a limitation called hop count. Hop count is the limitation. 15 hop is the limitation. Now, RIP uses metric. What? Just now we saw. RIP decides to go via router 2. Why? It uses a metric called hop count. It compares the hop count. If I go via router 2, it is 2 hop. If I go via router 3, it is going to be 3 hop. 2 is better. So it will put this route into the routing table. Even though router 1 knows that there is another route, even though router 1 knows that there is another route via router 3, it will ignore that route, because when it compares the metric of these two paths, which is a hop count, the hop count via router 2 is smaller. So what is the metric? Based on what it measures, based on what it decides the best path, it is based on the hop count. RIP uses hop count as a metric. Hop count as a metric. Smaller the hop count, better is the route. Lower the number, better is the route. Did you understand the metric
Yes, sir.
point, hop count? Okay.
Yes, sir.
And the maximum hop RIP supports is 15. And the number 16 hop is an infinite metric. Infinite metric is 16. Meaning any destination on the 16th hop, the RIP will not take. According to RIP, the number 16 is unreachable. RIP don't like 16. It knows it likes only up to 15. That is why I said if your environment has got like 10 to 15 hops, you can have this routing protocol. Because the 16th hop, if you will have, the 16th hop cannot be learned by the 0th router. Sixteen is an infinite metric. We'll talk about this thing more in detail after some time. It's coming. Right now, this RIP is a protocol which is going to use a no. There are two versions that I need to say. RIP has got two versions. Version 1 is a default version. Which is class full. Version 2 is classless, which is not default. You have to switch from version 1 to version 2 if you need this advantage, classless. Now, what is class full and what is classless? Class full means the protocol that advertises only the default class full network. Classless can advertise the network as well as the subnet mask. Classless protocol, they advertise and they consider both network and the subnet mask. What does that mean? If you have 10.1.1.0/24, it considers this network with this subnet mask, with this prefix link. According to version 2, the network is 10.1.1.0/24. But if the same 10.1.1.0/24 is now with version 1, version 1 will not consider these things. If it finds 10, then it understands that 1000. It won't consider this network, subnetted network, because it don't understand this classless. This is classless. 24 is classless. Actually, 10 means what? /8. This is the default class. This is class full, class A. 10 means it is class A. According to version 1, it is a class full. So they don't care about the mask. Whatever the mask that you may be having, actual mask that you configured is 24, it don't care about the 24. It simply considers as class A. But even though it is not as per the class, even though it is subnetted, version 1 cannot understand your subnetting. So it will simply advertise 10 instead of 10, 1, 125. It's not more granular. Version 2 sends the actual subnetted, that is why I say consider actual network and the mask on the interface that you have configured. In our today's world, we have everywhere subnetted network. Because our network, the world is big, we cannot have classical networks. We take one network and we try to break down into multiple networks and we use it so that we can support the large network. Everywhere there is a classless topology. So version 1 is not a suitable version. The default RIP version is version 1. We always switch it to version 2 so that the network that we have is classless. The classless networks needs a classless routing protocol. Version 2 is a classless routing protocol. Version 1 is classful. Now, what are the things that we have learned so far? RIP is a distance vector routing protocol. The maximum hop the RIP can support is 15. RIP's metric is hop count. The infinite metric in RIP is hop 16 is the infinite metric. Version 16, hop 16. 16th hop is an infinite, unreachable metric. RIP has got two versions, version 1 and version 2. Version 1 is a class full default version. Version 2 is classless. And the other difference in version 1 and version 2 is version 1 uses a broadcast address to send updates. It uses the broadcast address to send the updates, whereas version 2 uses a multicast address. And which is good. Using multicast is good. Broadcast address is the address that will carry the traffic to updates to everyone, even to those that don't want it, even to those devices that don't run RIP. The RIP's update, the RIP's advertisement, the RIP protocol's advertisement should go only to the routers that run RIP. But when you do broadcast, when this version 1 does broadcast, it will take the update even to those routers which don't run RIP. If you have some printers in the network, even the printers and scanners and your laptops will get the RIP update, which they are not going to understand and they are going to drop it. So sending to a broadcast is a bad idea. Version 1 is a flaw because version 1 is a classful protocol. Second reason is it is using a broadcast address in order to send update. Whereas version 2 is a classless routing protocol. It uses multicast instead of broadcast. Multicasting is identifying the group member and sending the updates only to that group member. Multicasting identifies the group, meaning all the routers that run RIP version 2 forms a group. All the router that runs RIP version 2, they are identified with one address, one multicast group. Now, when an update is sent to that multicast group, only the group member receives it, others don't. This is wonderful. Sending to only those routers that runs RIP is possible if you are sending the updates to multicast address. Version 2 uses multicast address. Now, so in short, RIP protocol has got two versions, version 1, version 2. This is default, this is configurable, and this is classful, this is classless, and this uses a broadcast address 255, 255, 255, 255 to send updates. And this uses multicast address 224.00.10. 9. 224.00.9 is the multicast address RIP uses. Meaning, all the routers that run RIP, they are the members of this group. You don't need to configure this address. They're already the members of this group, like, human being. When we say human being, it includes all men and women. We don't need to say this body, this is a human. Anyone born from a mother is a human being. Born to a human is a human being. Likewise, every router that is of version 2 is a member of this group. You no need to say, hey, version 2 router, you from now, member of 224.0.0.9. No, not necessary. You no need to think about this. You no need to care about this. No need to worry about this. It is by default, it becomes the member of this group, 224.0.0.9. So when anyone sends any update to this address, only the group member receives it because they are already a member. They say, hey, we are the owners of this group. Whatever you send to this address will belong to us. No other routers can receive it. That's the power of multicasting. Even though there are many devices, only those devices that runs RIP version 2 can take this and process it. Others cannot. That's a wonderful thing. Whereas version 1 sending an update to a broadcast takes the packet to whosoever receives it. That's the meaning of broadcast. Whosoever receives it. If the printer receives it, printer will also now try to process this. But again, they don't understand it, so they drop it. It's a waste of process and dropping. Now, these are the things that are different in these two versions. The common things are both do not discover neighbor. No, neighbor discovery. They don't discover neighbor. They never discover neighbor. But they still trust each other. How? You see, about topology, R1, R3, and R2, they are not really neighbors. They are not neighbors. They don't discover neighbor. So they don't know as neighbor. But the route that is advertised by router 2 is still maintained in the routing table. It is because there is a periodic update. Every 30 seconds, all the routers will advertise their best route from the routing table. Every 30 seconds, every 30 seconds is what called as periodic update. Periodically, every 30 seconds without delaying. All the routers should advertise their routes every 30 seconds. All the RIP running routers from the routing table, they need to advertise their route. What do you see in the routing table? The best routes. So every router advertises their best route from the routing table every 30 seconds. That is the one which gives confidence for the other routers to still pursue using it, continue using it. It is not based on the trust, it is based on the update that comes every now and then. For example, if you're waiting for a flight that is getting delayed every now and then, you're supposed to take off by 5 o'clock in the evening, and you got an announcement due to weather condition. The flight did not take off on time on the origin place. So 2 hours delay. That means 7 o'clock. We are going to take off. See, the one who is announcing, you don't know them personally, you do not know them personally, but you still trust them and wait for another 2 hours, hoping that the flight will take off. If they did not do that announcement, then you get angry. 5 o'clock I supposed to fly, but still the gate is not ready. The gate is not announced. But because they informed you at 5 o'clock saying 2 hours delay, the weather is bad. So you are patient now. You're adjusting yourself. You don't trust. They're not your neighbors, but still you, because of that announcement, you hope that the flight will be taking off by 7. At 7 again they announce you another 1 hour delay. Sorry for the inconvenience. The one who is announcing you is not a neighbor. You did not form neighborship, but you still hold it as a valid update because they are periodically doing it, updating you. Periodic update is every 30 seconds in RIP. That gives the confident to hold the root as valid. Even though we don't have neighborship, the root given by the adjacent router, the nearest router, you still hold it because he's keep on telling you that 4444 is too hop, 4444 is too hop. He's keep on telling you every 30 seconds. So you hold it. You still keep it as a valid route via router 2 to reach 4444. We call this periodic update. I'm repeatedly saying the same point for a long time. The reason is this: there is no neighbor discovery. That should be well understood here. All other protocol, routing protocol, discover neighbor. RIP never does it.
Yes, sir.
RIP never does it. RIP, they don't discover any neighbor. They don't form neighborship. You will not see any neighbor table. But the routes are still maintained because every 30 seconds the adjacent routers advertises it. So this is again, so a common thing, let me write it down in the middle. Periodic update. Every 30 seconds. What if this periodic update is not coming every 30 seconds? It's supposed to advertise my adjacent router. He's supposed to advertise 4444 is one hop away from me every 30 seconds. If it is one hop away for router 2, then router 1 will say, okay, it's 2 hops for me. So this happens every 30 seconds. This confirmation happens every 30 seconds. But what if this stops? So if this update stops coming, what action router 1 should take? Actually,
The routing table will be updated on R1 saying that the R2 is down.
yeah. But there's a period, time, waiting time. Wait for all the time. There is 180 seconds. You see, when an update is not coming, the router will not immediately remove the route from the routing table. It won't immediately remove. See, if router 2 stops saying, maybe something went wrong. So router 2 is not saying. Router 2 might have found that 4444 is no more available. Why? Maybe this link has gone down. But router 1 will not immediately remove it. Maybe some traffic jam, so packet might have lost. The update might have got lost. So it will wait patiently. See, meanwhile, this is also advertising. Router 3 is also advertising for me it is 2 hop. Then router 1 will say it's 3 hop for me, but I have something better which is 2 hop. So let me hold it. So it will hold it for how long? For 180 seconds. 180 seconds it holds this one. Even though the update is not periodically coming, It is holding this one because the hop count is less. In olden days, the network was not this fast. The network was not having this much bandwidth. So packet getting lost, updates getting lost is very common there on those days. Was very common. So they said, RIP, don't decide immediately. Wait and confirm. So waiting and to confirm, it takes 3 minutes. After 3 minutes, the routers will understand that the network is possibly down. As soon as they understood that it's possibly down, instead of advertising as one hop, now it is going to advertise a 16 hop. 16 makes this router to understand it is possibly down. This router 2 waited for 180 seconds. There was no update from this router, let's say router 5, about 4444. Every 30 seconds it's supposed to give, but it did not give for 180 seconds. So what router 2 does is, after waiting 180 seconds, it decides that this network must be down. To inform that network is down, what it does is, it puts hop count 16 instead of 1. Why it puts 16? So that the router which is receiving it will know it is possibly down. 16 means what? Infinite metric, an unreachable metric. So router 2 uses the number 16 to alert router 1 that don't trust me anymore because I waited 180 seconds and I found that 4444 is possibly down. So what router 1 will do, it will put it in a possibly down state for 60 seconds. Everyone will put, as soon as they receive that 16 hop count, they wait for another 16 seconds, which means earlier it is 120, now it is another 60, which is 240 seconds. They flush it out. The flushing interval is 240 seconds, meaning removing the root from the routing table happens only after 240 seconds. The network gone down 240 seconds before. Now only the root gets removed from the routing table. Listen, only when this root gets removed from the routing table, this root can enter in. From now on, router 1 will point towards router 3 to this destination. You see, it takes 4 minutes. It takes 4 minutes for throwing the bad root from the routing table. Only when the bad root is thrown out, another route can come in for the destination. For that destination, even though the alternate route was available, router 1 was not able to use it because the bad route is still there in the routing table. It is there because according to RIP, it has to hold it for 180 seconds. And then after finding it as possibly down, they have to stay in possibly down state for 60 seconds. And then only they have to flush it out. Because on those days when RIP was introduced, designed, the networks were very slow. This delay was not a big delay. It is very, very bad delay now. On those days, it was not a big delay. On those days, going to a bank and withdrawing money will take 1 day or half a day at least. That was not considered as a big delay on those days. Today, no one wants to spend half a day for withdrawing money. If the ATM doesn't function, they go to another ATM, another ATM, another ATM, another ATM till they get the money. They don't want to wait. Likewise, the network has grown bigger, faster, more bandwidth. So this delay is not an acceptable delay. It takes 4 minutes for router 1 to take another alternate path to route my packet. In this 4 minutes, there may be 4 million packets dropped by this time if it's a large network. And I'm just telling very small number, not 4 million, will be 40 million also if it's a large network. Again, it depends on to what server or what destination the packet is going. Anyway, what I'm trying to say is the convergence is very slow. This is one big drawback of this protocol RIP. Slow in convergence. Whether it is version 2 or version 1, the convergence is slow, not acceptable, slow. Can we change this timer? Of course you can do it. You can change these intervals. They have to do it on all the routers. That is recommended, not mandatory, but recommended. Only then there will be a sync. You can change this. Even if you change this. Compared to all other routing protocol, this is going to be slow in convergence. So, one thing we should understand is this protocol is slow and steady. I'm not saying bad protocol. When someone teaches RIP, I hear them saying RIP is bad, RIP is bad, RIP is bad. No. RIP protocol is also a good protocol. Of course, ship is taking a long time than an aeroplane. But still, ship is very important to carry cargo, which an aeroplane cannot carry that big. So RIP is an important protocol in spite of all this. Fine. Now, these are the common things. Now, about RIP, there is two more points to be learned, which is called route poisoning and poison rivers. To understand this, we also need to know there is a rule which is not of RIP actually, which is a default rule. But to understand this, we need to understand that. What is that? Split horizon rule. Split horizon rule. What is this rule says? Split horizon says The route learned on a port can be advertised via other ports but not on the same port. What does that mean? This direction, I'm getting an advertisement about 3.3.3.3. In this direction, I'm getting advertisement about 2.2.2.2. 1.1.1.1. Let me name this interface E0, E1, E2. This 3.3.3.3 advertisement that I'm receiving can be forwarded via E1 and E0, but not back on the same port. The networks that are learned on a port cannot be advertised back on the same port. So this 333 will go this way, but it won't go the reverse way, the direction from where it has come. Not possible. Likewise, this 111 can go E1 and E2, but cannot be advertised back via E0. Listen, I told you the router will advertise the routing table every 30 seconds. So router 1 will not advertise about 3333 in this direction, even though it is there in the routing table. Even though it's supposed to advertise the route from the routing table, all the routes in the routing table, this route that is learnt on this port will be filtered from advertisement. Every 30 seconds it does periodic update, right? Periodic advertisement. In that advertisement, you will not see 333 when it is sent in this, when the advertisement is sent in this direction. You will see 2.2.2.2 sent every 30 seconds, 1.1.1.1 every 30 seconds from the routing table. From the same routing table which has got 33333, it won't advertise this from the routing table on this port because that network was learned on the port. That 3333 was learned earlier on that port. So should not be advertised via the same port. What prevents this? That is what called a split horizon rule. Split horizon rule. Now, what is the connection between this and the below 2 points? Poisson rivers have got some connection. Let us first learn route poisoning. What is route poisoning? See here in this above diagram, this router 4 stopped advertising about 4444 for some reason. Stopped advertising. How long router 2 was waiting? How long router 2 was waiting to consider it as possibly down?
3
Yeah,
minutes.
180 seconds, 3 minutes. After 3 minutes, what it does is it puts 16 hop instead of 1 hop, and it will advertise to router 1, which is called route poisoning. It is poisoning it. If it is 1, it will be a valid one, but it do not want it to be 1 because the route is no more available this way. It is router 2 has found that the route has disappeared. It's no more. So it needs to poison it so that no one will use it. To poison it, it puts 16 and advertise to R1, and R1 immediately understands that the network is possibly down. See, R1 was not waiting for 180 seconds. It was only R2 waiting for 180 seconds because R2 did not receive the update from R5. So during this 180-second, R2 was still sending every 30 seconds the update without any problem. Sorry, as if there is no problem. But as soon as router 2 waited and found that the network is down, it immediately puts 16 and informs to R1 so that R1 need not wait another 180 seconds. R1 will simply wait for another 60 seconds and remove the route from the routing table. It is because of the route poisoning. Router 1 poisons the route as soon as it learns 16. And the poison route will be there only for 60 seconds. Then it will be vanishing. It will disappear from the routing table. It will get disappeared from the routing table. Okay, that is route poisoning. What is poison reverse? Poison reverse is router 2 going in this direction, which is not allowed earlier. Split horizon never allows. Split horizon says you should not advertise about 444 in this direction. That's what split horizon says. But overriding that rule, after waiting 180 seconds, R2 overrides the split horizon rule. Same like as it sends 16 hop in this direction, it is also sending 16 hop in this direction for the network 444 to reconfirm with R5. It is going to the source, overriding the split horizon rule with the poison, with hop count 16. This is what we call it as poison reverse. It's going in the reverse direction, which is only possible for those networks found as possibly down, not for any other networks. The other networks, split horizon will not allow them, will prevent them. But only for those routes found as possibly down, split horizon is liberal. Split horizon is quiet. Split horizon allows for this network to go back to the original source to reconfirm that the network is surely truly gone. Right? So route poisoning and poison reverse can be asked in the interview. If someone wants to ask something very tough in RIP topic, this is what they will ask. They'll ask poison reverse, they'll ask split horizon, they'll ask poison reverse, route poisoning. Other things everyone knows, so they don't ask too many things like what is the what is the periodic update? Who knows? That is also a nice valid question. But most of the people who say they know rape, they're not clear with these two things: route poisoning and poison reverse. Right? So we have learned almost all about this one protocol called RIP. What is left is the lab part. Today we are going to do a small lab, and in our next class we'll
Yes,
do a
sir.
detailed lab on RIP. Today what we are going to
Okay.
do is we are going to take the same topology where we had the static route, and we are going to remove the static route and enable the protocol RIP. Before that, I want to tell something. What is that? For static route, we need to know the complete topology. If you know the topology, only then you can write static route like this. Show IP route. Because you know the topology, you very well said, because you're very clear that 10 is via this neighbor, whereas 40 is via the other neighbor. You know the topology well, that's why you did this. You can write this. You know 40 is via 30 is via router C, that's why you wrote this. And you know 10 is via router A, so you wrote this. But I told you for dynamic routing protocol, you don't need to know this. All you need to know is what is on that router. You don't need to know about the networks on the other routers. Not necessary. All right. So we are going to remove the static route which we have already enabled. This two I'm going to remove. Likewise, I'm going to remove the default route that we wrote here. And also from R1. Control A will take your cursor to the beginning of the line. Control A. That's how I went here and I put no. Now, I don't have routes. Show IP no routes to the foreign networks. Show IP route, no routes. Show IP route. I was telling you that when you want to enable a routing protocol, you need to know what network on this router. On this router, I have 30 and 40. You see, I go to global configuration mode. I say router RIP version 2. Not necessary. I don't want to say version because all are classful in my network here. In our next lab, we will do classless version 2. So today we are going to do the default version RIP. And I need to simply say network 30. Means I'm telling if you find 30 network in this router, advertise it to others. Network 40. That's it. Likewise, you go to router B, router RIP, network 20, network 30. You don't need to write about 40 network and 10 network here. They don't belong here. Now go to router A, router RIP, network 10, network 20. So don't write about 30 and 40 here. That's all. You have successfully configured protocol RIP. And now if you go and check the routing table, you will find the routes there. Yeah, you're going to find the routes there. Let's check. Show IP route. Ta-da. But RIP giving you the route to reach 30, which is one hop away, and this is the gateway, and this is the exit interface. What a beautiful output. See what all RIP shows. It shows the exit interface, it shows the next router to where it needs to be delivered, and it also says hop count. Now for RIP, the administrative distance is 120. You remember I told you for static route, if you say next to hop, then the administrative distance is 1. We saw that 1. For
Yes, sir.
directly connected, it was 0. Now for RIP learned route, what is the administrative distance? 120. Why 120? Don't ask me. Because 120 is what Cisco has given for the RIP. This is the level in which Cisco respects RIP. Every vendor has got different number. For Cisco, the importance that they have given to RIP is 120. For static route, 1. For RIP, it is 120. Likewise, for every protocol, then there is a number like OSPF 110, EIGRP 90, IBGP 200, EBGP 20. So there is a administrative distance value for each protocol. Means that's the preference value. That's the level in which you trust the protocol. Don't worry about this number. This is predefined by vendors. They are not same for every vendor. Now this 40 network is 2 hop away. You see that this is why we call this a distance vector protocol. It says 40 network is this far. How far? 2 hop. In which direction? In the direction where F00 is. In the direction where 20002 is. Distance vector. Now, if you go to router B and check the routing table now, and you see 10 is in this direction where 20.001, whereas 40 is in the other direction where 30.002 is. Distance vector. You see, it shows the hop count in the bracket, 1 hop away. 120 by 1. 120 is the administrative distance. This can be changed from 120 to any number that you want if you wish to. If there is a reason, you can do that to change it. And now let's go to router C and check the routing table. Show IP route. Here also we have 10 is 2 hop away, 20 is 1 hop away. Now let me go here and try pinging 40. I should be pinging. You see? It pings. Not only the PC, you can ping the other IP address like 30.002. You can ping anyone in the path. Ping 20.002. So you got routes for every destination here, right? So we have successfully covered the theory of RIP, and we have done a small lab in version 1 RIP. What is following next is version 2 scenario, which is a classless. We need to have a different topology where we'll have a lot of subnetted networks. There I'll show you how important it is to switch to version 2. And we will also see there will be different address used to do the advertisement. For version 1, it is going to use a broadcast address. Version 2, it is going to use a multicast address. I'm going to show you those things in detail in our next class. Do you have any question on what we have learned today?
No, sir, no questions.
Wonderful. So I hope you enjoyed the